Our next speaker is Amos Storkey. And Amos is the professor of machine learning and artificial intelligence in the School of Informatics at the University of Edinburgh. His research is on machine learning, reinforcement learning, and language models. In particular, he looks at forgetting in continual learning. So he will be talking about the art of forgetting today. The stage is yours.
Great. Thank you very much. Thank you very much for inviting me. I hope you're enjoying the workshop so far. Had a good time. It's been good meeting people. It's a lovely chance to get together. I hope to be a bit different here. I know in a modern world, I'm competing with your email and your phone and whatever for attention. And rightly, it's my job to be more valuable than those other sources. So I'll do my best. I want to talk about continual learning, but I want to talk about continual learning in modern AI settings. And the part that we all play in actually that process. So I want to make the case that most interesting AI problems are actually continual learning problems. And I want to make the case that continual learning is really instead an attitude. It's a way of thinking about problems. It's a way of asking quite particular questions that we care about in different settings. So continual learning research is then asking, how do we make the right use of the information that we have in complex, open, or long horizon or unfolding settings? So that's the sort of thing that we're going to be looking at. So I also want to make the case that forgetting is key in this whole process. So I'd like to, please do interrupt. So if I'm saying something that you disagree with, it's all on camera, so if you ask a stupid question, it'll be a stupid question on camera. But luckily, the camera's pointing at me, and I'll be saying stupid things that are probably much more stupid than the questions that you ask. So you're okay. So do interrupt, ask questions. It's a workshop. This is not like anything formal. So let's do it that way. Is that working? Oh. Let me first introduce the group. So this is the Bayesian Neural Systems group in Edinburgh. So a lot of the things that I'm going to be talking about, we will have discussed in group meetings, argued about, discussed over pints in the pub, whatever it is. So, you know, in as much as they're my ideas, they're probably everyone else's ideas too. So some of this work is specific work of others. I'll acknowledge the authors as we go through. So I'd like to start by going back, way back. So right back in time, the problems of continual learning are absolutely not new. And forgetting goes back as long as we have been doing learning. So I'm going to start with Hopfield networks. So who here has bumped into Hopfield networks ever? Of the small number of people who put up their hands, who would have bumped into Hopfield networks if a recent Nobel Prize had not been awarded? a few, okay. So I'm going to go back to Hopfield networks. And so here's the problem, for those who don't know. What we're going to be given is an online sequence of binary vectors. So it's a nice, big, long binary vector. And I'm going to give you a sequence of those. And I'm going to give you that sequence in an online fashion. And we wish to train a model to model that distribution of the vectors. And the reason we want to do that is that at test time, I'm going to give you a noisy version of one of the vectors that we maybe saw, and I want you to be able to give back to me the correct thing, what it was that was originally provided. So in that sense, Hopfield networks are called a content addressable memory. So in Hopfield networks, training progresses according to a Hebbian learning rule, which is incidentally quite like a stochastic gradient rule. Not exactly, but it's not far off. And it takes one data point at a time and adapts according to this rule. But here's the rub. After a while, training on new data causes the ability to recall all the old data to suddenly collapse. So here's the graph. We start here, and we're busy adding training data points on the x-axis. And then we look at what we can recall of those training data points on the right axis. And it goes up and up and up to some point when suddenly everything collapses. So this is called catastrophic forgetting, real catastrophic forgetting, not the catastrophic forgetting that most continual learning people talk about, which is a bit of a misnomer. In continual learning, forgetting is, well, really just forgetting. There's nothing much catastrophic about it most of the time. So the problem of hot field networks is exemplar of what's going on there. And it's a kind of destructive process. We know what's going on in hot field networks because they're really simple. But it's a destructive process. We have a situation where as we train each of the different memories in there, they produce noise for the recall of the previous memories. And that noise builds up over time, and eventually that noise overwhelms the signal, and everything then starts collapsing. So way back in time, I was working on these in my PhD, and we developed a learning rule, which has since become called the Storkey learning rule, which fixed this in two different ways. One of them is it reduced these interference mechanisms so that it really amplified the number of things, the storage capability of hot field networks, minimized the amount of forgetting that was in there, and it also removed the kind of more catastrophic element of that. So it allowed us to control when forgetting happened and make sure that more recent memories were still stored, even if I was forgetting older ones. And so my argument is that modern forgetting can actually be thought of in a very similar sort of way. We can think about it in terms of these signal-to-noise analyses as to what is happening within those scenarios. Also, back in the day, this exemplified something that is pervasive in all learning, which is the stability-plasticity dilemma. So a stability-plasticity dilemma asks the question, do we favor storing new things at the cost of losing old stuff, or do we want to maintain the old stuff while reducing our capability of storing new things? And at the end of the day, if we have a fixed capacity, we have to do one or other of those eventually. And in some senses, modern scaling laws and foundation models try to overcome this just by making things so big that we can store effectively the whole of the internet in our models, and so we have capacity for it, so we don't bump into the stability-plasticity dilemma. So that's hot field networks, and in a certain sense, that's a precursor for a lot of the problems that we see in continual learning down the ages. So forgetting then is ancient, it is pervasive, and much of the work in continual learning is trying to come up with methods that overcome forgetting in some sort of way. But I'd like to ask, are we doing it right? Are we perhaps building fixes to forgetting without really knowing what the problem of forgetting is? And of course, when you ask a question in a talk, you're not really asking a question, you believe there's an answer, and I'm going to argue it to some extent. Sometimes, yes, we are doing that. And so I'm going to make, first of all, a couple of observations about continual learning process and the received wisdom in continual learning, and then we can go on from there and look at it in current contexts. So the first of these issues we'll call chunking, and let me put it this way. So the received wisdom in our field is that forgetting is caused in continual learning by task shift or distribution shift. So that is, we're learning and we might have some kind of class incremental settings, so we see some new classes that we hadn't seen before, and we're not seeing old classes, and because of that shift, we start forgetting the old things. Okay, so that's the wisdom. So the data here is arriving in chunks, it's arriving in batches, and then sometimes the task shifts between batches, and we have to now train on those new tasks. But is it? Is that what's going on? What happens if we train on the same data with the same distribution and the same chunking, but remove all the task shift or all the distribution shift there. So this is what Tom Lee did in the paper that's being described here. He basically took the data that we would normally train on them and reshuffled it now so that each chunk was all sampled from the same distribution. And we can now rerun all our continual learning experiments in that sort of setting, optimizing one chunk at a time. But then once we've seen one chunk, we don't get to see it again. And it turns out, if you do that, if you go to the chunking setting without any distribution shift, what you find is that the loss associated with that, compared with full batch learning, where you get to see all the data as much as you want, actually, the loss associated with the chunking setting explained about 50% of the total loss on standard problems compared with that task shift continual learning setting. What's worse, most continual learning methods completely failed to improve the chunking loss. They only ever dealt with the task shift issue. So actually, forgetting is not all about task shift. It's as much about the fact that we only see things in this incremental way, and we want to do this online learning as part of that. Next up, we've been talking about forgetting for a long time. But what do we actually mean by forgetting in continual learning? Quite often, it's talked of as if it's basically some sort of reduced performance due to the fact that we are doing things with task shift or in a sequential way or whatever else. So we basically measure performance, but performance loss can be a result of many different things. It can be a result of not learning in the first place, not needing, it can be a result of forgetting things, it can be a result of many different features that play a part in that. And we need to know how we can actually think about forgetting and decouple it from those other things. Why do we want to do that? Because if we can understand forgetting and account for it and make sure we only forget when we want to, then we can improve our learning algorithms in that sort of way. So we want to examine forgetfulness as a property of a learning algorithm. That is what we're about. So how do we do this? So how does learning work? Let's just encapsulate learning. We might have a learning agent, and let's call the state of the learning agent Z. Okay, so Z is I'm a learner, my state of affairs is Z. And what happens is I then see some new data, and we'll call that X. So I'm Z, some new data X comes along, and I observe that data, and then two things happen. One of them is I change my Z because I'm observing that, and I've now gained new knowledge from X, and quite rightly, I should then change my opinion. But secondly, I'm moving from my old opinion to my new opinion, and that move might involve forgetting some stuff that I knew before, but I'm forgetting it because I'm doing the learning. So those two things are coupled, the learning, the acquiring knowledge, and the forgetting old knowledge, are all coupled together in that single learning step. And it's really hard to know how to decouple those two things. So how do we understand our state Z? Well, the only things that matter in Z are the things that we use for, in a certain sense, the future. How we might produce class labels in the future, how we might predict the future, and understand how that future unfolds. So it's that future that matters, and that's what we'll be looking at as we analyze how to understand forgetting. So the focus here is on our predictions of the future, and forgetting is then losing information that we previously had about that predicted future. We're not too bothered about the correctness or otherwise of those predictions. It's a kind of subjective look from the view of the agent. How is that information changing within the agent? We can measure information change quite easily. There are divergences like the KL divergence that can measure change in information. So if my predicted future changes, I can measure that. But we have to decouple somehow this learning and forgetting process. How can we do that? Can we do that? And it turns out that we can, and we can do it in the following way. Suppose we have some predictive future. Suppose we have a process now where we generate data from the next step of that predictive future. We generate fake data, not the real data that we will later see, but just some fake data. Now, that fake data is now generated from the distribution I already believe. And so suppose on each of those fake data items, I now take a training step, and then I average across all of those items. I'm not actually training on any new information. I'm just training on what I already believed. And so on average, my belief should not change. I should be in the same belief state as I would before I did all that training. Turns out in 99.9% of learning rules or learning situations, that doesn't happen. What happens is there is some shift. What is that shift? Well, I've got no new information, and I've changed from one belief state to another belief state. And in doing so, the only thing I can do now under the data processing equality is have lost some information. So actually, I can measure now my loss of information due to the forgetfulness of my algorithm by computing the KL divergence between what I believed before and what I now believed, having gone through that fake training regime on my fake data. So suddenly, I've now got a method for analyzing forgetfulness in my learning algorithm, and I can say something about that. And so all we're doing is we're taking our Z, producing predictions, training on those predictions to get a new Z, and then computing that. And we can then score that empirically using samples to score our learning algorithms in particular scenarios to work out how forgetful they were. And we go into more detail in the paper as to how that works. So one consequence of this construction is that, and we prove this in there, is that Bayesian learning is non-forgetful. For our definition, we prove it in the paper, but it's kind of obvious. And one way to see how it's obvious is the following. If you think how Bayesian learning works, is I have a prior, I see some data, I update my prior from that data, and I can do that sequentially, one data point at a time, to get down to a final posterior. And what is that posterior? That's the posterior having seen all that data. Okay. That's the same as what I would have got to if I just seen all the data at once under a Bayesian probabilistic formalism. But it turns out that I could have done that in a completely different order and seen the data in a totally different order, and I'd come to exactly the same posterior. So my posterior is order independent on that data. And so if you think about it, that means that every data point is effectively the last data point you saw. And that last data point you saw, you've just learned on. You haven't had any chance to forget anything yet because you've just learned on it. So effectively, for every data point, you can't have forgotten it because it's the last thing you saw potentially under some ordering. So Bayesian learning is not forgetful. Bayesian learning has many other problems that make it hard to leverage in continual learning context. But I think that every continual learner should have in the back of their mind a Bayesian learning processes and understand that as a kind of way of thinking your way into a given problem or a given setting. Forgetting is not always bad because there are times we really do need to forget. Some of those are kind of outlined there. I'm not going to go into more detail on that. And a bit of the rest of the talk is about these times that we might choose to forget. So again, the settings in which we might really care about forgetting are also varied, and that gives us some indication of the things that we might care about. But the key thing here is that control over that forgetting is quite important in that process. If it just happens and we have no control over it, whether we care about unlearning, we need control over it. Whether we care about continual learning, we need control over it. It's really knowing how to manage that forgetting. Okay, so we've spent some time talking about core issues in continual learning. We've demonstrated that they're potentially pervasive. They cover a lot of settings. But the next question is, have all these problems been solved already in modern machine learning. So in a modern world, practitioners, researchers may well fall into one of three categories. You may be foundation model builders of some sort. They may be foundational model adapters of some sort. They may be foundation model users of some sort. But ignoring heavily trained models trained on vast amounts of data and just kind of going, oh, no, ignoring those, that's probably not what we want to be doing if we want our methods to be effective. So where are we left with in continual learning? Well, in a certain sense, prompting is learning. We have in-context learning in these large models. Modern context sizes are massive. You know, you can pipe a lot of information into those contexts. Attention has access to the full history of that prompt, so I can pick out different bits of it. Even if it's not in the prompt, I have access to RAG and other forms of tooling that can pull in information from anywhere in the internet and add it to what I have and handle that. So in a certain sense, what's forgetting when you just have the whole of the internet as your memory? Really, is continual learning a problem anymore? And in fact, we can press on with this. There isn't a capacity issue. Basically, our models are so big that the idea that we have capacity kind of constraints, we really have to worry about. Task shift, well, task shift is just contextualization. You know, we have a big model. We now contextualize it to our current task. And hey, presto, we've solved task shift. That's not a problem anymore. Forgetting's not an issue because everything's just in context. And in-context learning is very good at not forgetting. It's kind of maintaining a memory of whatever's going on. Even when we're doing learning, the way transformers are, the sparsity of activations in transformers and therefore the sparsity of gradients within those transformer settings mean that you have slightly more orthogonalized gradients. Forgetting is much less of a problem, which is why we train our large transformer LLM models just continuously on new data, and it kind of memorizes the information that's in that. It's why our large language models seem to know a lot about everything, because even though they've only kind of seen each thing once, because they're kind of consolidating that and picking that up. So they learn pretty well. So are we just basically out of a job? You know, and we're all here, and we're just here because we're pretending to go to work when we've already been sacked, 2 years ago. Is that the situation we're in? Because we can't just ignore it. We can't say, oh, we're just business as usual, because it's not business as usual. We do have to ask ourselves, what does continual learning mean in the settings that we are in the modern world? So where is continual learning nowadays? So here are a couple of slightly modified, because, I mean, who knows, the reviewer might be in the audience, of reviews that I have, or snapshots from reviews I've seen in continual learning settings relatively recently. So top one, my major concern, it's big, major concern is lack of experiments evaluating the proposed method in the class incremental setting. And then, again, it's unclear how this framework fares against state-of-the-art CIL baselines. I mean, really? Is that your major concern? I think, and my analogy is in that slide, it's like being obsessed with slide rules in the age of computers. I mean, let's get over it, people. We need to move on and get on with real problems that the world cares about. So that's my kind of, punch here. I really think we need to kind of focus on that. And this is where I'm going to kind of play the card. I think I'm going to argue that continual learning is still relevant. There's a phoenix and it's going to rise from the ashes or something. I'm going to argue it is still relevant, but we do need to kind of get our heads out of the sand and actually face it where it's at. So at the end of the day, lifelong learning is still an ambitious problem. So let's face it, it's not a solved problem. It's an ambitious problem. It's an interesting problem, and it's a key problem. So we've got to come to that. Foundations models are very helpful, but they are frozen snapshots of some sort. RAG and other applications mitigate this, but they don't solve it entirely. They're useful, but they don't solve all the problems. There is the size issue. You know, you'll see people, they'll say, oh, well, I care about embedded devices and things like that. Using full foundation models for everything can indeed be like using a jackhammer to hammer in a picture hook. So we do have to be careful there. And also, currently, foundation model providers are subsidizing our use of these things by massive tunes. So if you think they're expensive at the moment, you wait until they're really costed, and then we'll see how expensive they are. So there is an issue there. Continual learning does involve constraint and thinking about constraints and those meaningful constraints. But those could just be constraints in cost. But it's important not to over-egg this because, you know, in a lot of settings, even our embedded devices have access to the internet. We can do things in ways that are kind of server-client models. We have to be careful not to overclaim the constraints we're under in any realistic setting. The other thing I want to point out is we can learn a lot in continual learning from modern agentic systems. Actually, if you look at, and the first talk today very much discussed this, we look at modern agentic systems, there's a memory management focus to what's going on there. And memory is, after all, what we're about. We're wanting to keep the right information. And in a certain sense, that is what a lot of what is going on in agentic systems. But there are many ways that we can focus our minds in terms of this for continual learning researchers. I put some of them there. I'm not going to go through them all, but that's what I think we can begin to look at. What I will do now is I will say a little bit about some things we've been working on in addition in the group, and why I think these are important in terms of continual learning. First up, let's look at foundation models kind of beyond transformers and beyond attention. So the key thing here is, if we're going to look at efficiency, foundation models such as vision language models need to kind of manage memory effectively, because if I've got a very large memory, I've got to work out what bits of that memory to use, etc. If you look at transformers, the effective state space of a transformer is the whole KV cache of that transformer. So if I want to view transformers as a state space model, I have to keep the whole KV cache, and then new data comes in, and I update my KV cache by kind of plugging that onto the end of my KV cache. I have to do a lot of processing to produce that new KV cache, but it goes in there. So that is the vast state space of a transformer-like model, and you're solving the problem by storing everything. And so the question is that the right way or the only way to go about it? And I think it's good to look at settings where we ask, can we manage that memory better? You know, this is an ad hoc choice to store all that KV cache. Are there better ways of doing that? And state space models take a different approach. They say I have an explicit state that I'm storing things in, a bit like the Z earlier on, have an explicit state I'm storing things in, and I'm going to update that state. So models like Mamba do that, but Mamba's a linear parameter state space model, and it doesn't perform as well as transformers on a broad variety of problems. So there's something missing there in terms of that. Now, I'm not claiming we solve all the problems, but one thing we've been working on is another model called Kalman linear attention. And for those of you who know Kalman filters, it's kind of basically the Kalman filter equivalent to Mamba. It's a kind of probabilistic formalism that tracks the uncertainty of the state as well as the actual state itself. And it turns out by tracking that uncertainty, you get attention mechanisms via kind of Bayesian computations for free, depending on the relative importance of different pieces of information coming from different sources. The fun thing is that even though Kalman linear attention is a nonlinear model in parameter space, it is still reformulatable using a parallel scan in the same way that Mamba is. So we can train them just in the same way of transformers or other things. We don't have all the problems that you have with a lot of other recurrent models where we can't parallelize things, and we're then stuck with backpropagation through time, which is going to kill us if we really want to do it at scale. So KLA then helps us by getting this kind of probabilistic state space formalism, which captures how much we know so far in a given setting. And the uncertainty elements of that are quite key because they capture our understanding of particular parts of that, and therefore our uncertainty about things in the future. And that uncertainty helps us to know what it is that we need to update going into the future. But also, like a Kalman filter, the transition from one time to another is a forgetting transition. So there's a controllable forgetting gate, effectively, that says how much we forget between time steps for each of the components of the KLA. So it has forgetting built in. It reduces things to a specific state space and manages things in that way. Memory management can be done at many different levels. Again, your summarization is a tool that can be used in LLMs, etc., for handling different sorts of memories. And dealing with these explicit memory management methods is quite a good idea. And in a certain sense, if you're looking at long horizon planning problems, for example, I need to have this summarization process where I take things, I do processing, I then summarize things. And what's more, we have to balance our reasoning capability with the new information that's coming in. We want to be able to reason on things or encourage reasoning, just not rely on getting new information all the time in order to solve all problems. So I think there are a lot of things, fun problems in that space that we can look at, that we can target as continual learning people and say, actually, this is really an interesting way we maintain information through time. Word or two about reinforcement learning. Reinforcement learning is the natural continual learning paradigm. Why? Because in reinforcement learning, at least in an online setting, and most reinforcement learning eventually becomes online, your policy is changing over time. That policy is a policy you're using to collect data, and so you have distribution shift as a natural built-in feature to RL. But one interesting question to ask is, well, what do you mean by the policy? Because actually, there's no reason to have one policy in reinforcement learning. Suppose we have a policy which is our exploitation policy. That is how we're going to do the best in a given setting. If our exploration policy knows our exploitation policy, it will choose to do something different from that exploitation policy to maximize the information provided to improve that exploitation policy. So actually, really, we need two policies. We need an exploitation and an exploration policy, and we can work out what the right exploration policy is by informational improvement measures on the exploitation policy. And that's what we looked at in the PT Good paper, which was planning to go out of distribution. Our exploration policy wants to go out of distribution in order to get more information to learn things that are going on. So that's very task-specific in an RL context. In task general learning, then exploration becomes even more key. And back in the day, we worked on random network distillation, which was a key method for encouraging this kind of exploitation. It was the first to provide full coverage of the Montezuma's revenge. So it kind of, at the time, did very well. There are plenty of other methods nowadays in terms of these kind of exploration-driven or curiosity-driven RL. But I think all these areas where we're looking at things beyond just simple reward policies, reward-driven policies is a good idea. The main thing I'm going to say a few things about now are world models. So world models matter in continual learning because I'm arguing they are a continual learning problem, and using world models is also very useful in a continual learning setting. So the idea here is that we need something to help us understand what we've learned so far. And the idea of just keeping some memory buffer as the optimal solution for knowing what we've learned so far seems a bit misguided, because it's raw data and we have to keep it at that, but we're constrained as to how much we keep. World models could help with that because they can keep us our current understanding state and allow us to develop things from there. So we worked a little while ago on developing kind of at pixel level world models. So this was work by Adam Jelly and others, a student of mine, that was one early diffusion-driven world model. So the idea here was we're going to use diffusion models as a mechanism for generating the next state. And that sounded expensive because we have to, every time we come to a new state, we have to generate a full diffusion of that. But it turned out we had a number of things that enabled us to do that a little bit more efficiently. And so conditioned on an action, we're asking what is the next state given the previous state we're in. And this is basically, what is a world model? It's an action-generated model of either a latent or a data space of how the future unfolds under an action sequence. And we could train this. We could train this on Atari and various other things. We also trained it on Counter-Strike, and we were playing let's get that running, playing various things there. And so we're allowing it to kind of generate things in Counter-Strike and play this. And so what you're seeing here is just a world model. There's no game engine there. It's just kind of generating it with diffusions as it goes along. Fun stuff happened. So we were talking earlier about physics and physics generalization. So is the model just copying what it's seen? Well, one way you can see this is that in a real world, I can't jump twice. So in the real game, but what happens if you jump twice or more than once in our simulation? Well, we find that it's never seen anything like this, but somehow it is doing some kind of vague 3D generalization for a bit before it collapses into a heap as part of what's going on there. So in a certain sense, these models are kind of learning things. But one of the questions is, how do we get these things into more long horizons so that we're actually continually kind of adapting things and continually using the data that we've seen before to drive things? So we took that a bit further, and that was then introduced, and we took part in the ICCV CVPR 1X World Model Competition. We managed to nail first place in both, and so this here is what we were doing. This was very much kind of humanoid robot world model sorts of things. And so we can see some fun examples. So here we see kind of an example, and I'm not sure if you can quite see, but you're kind of picking something up and putting it in there, but it disappears a little bit as it goes in. So it's quite fun. You've got a generated model here, but it has to, so we've got the generated one on the right, but it has to kind of make up stuff that it hasn't seen in the top right corner there. So it's seeing things that are not actually there, but it is generating realistic sorts of settings. Another thing we're looking at the world models is we want to focus in, not just on the whole thing, but focusing on particular objects to summarize those objects in those sorts of settings. And so we were training this again on other games. This is on Hollow Knight, and we're looking at how we can focus in on the different parts of the world that really matter and ensuring those are encapsulated. And so the attention maps on there are kind of the attentional things that we're focusing on as part of that. More recently, we're looking at ultra-long trajectory world modeling. This is as yet unpublished, but it'll come along in a minute, quite soon. Let's set that running. So this is kind of Oasis doing some runs in Minecraft, and you can see that nothing happens initially because I'm not doing anything, but when I start moving, things start moving around, and it starts to explore that environment. But what happens is what happens in most of these sorts of world model settings is it quickly goes to mush, and you end up kind of, in this case, in the long grass. But all sorts of things can happen in these sorts of world models. We've developed a kind of new, well, this is, I've got this started, it has started, approach for handling the diffusions in this particular case, for trying to ensure that we get these kind of coherent long distance trajectories. And actually it turns out that we can keep going and keep going, keep going in this, and you're getting kind of realistic generations in that. There are still some problems that kind of begins to get a little bit more boring over time, so it's not capturing the full variety of there. But at some point, I was impressed that is it going to show it? I don't know. A sheep arrived and started walking on the screen. That's rare in these sorts of world models to get these incidental things. There it is. You know, so even weird things are happening there. But yeah, that's quite fun. And so I think these world model issues are really coming along. But one big one there is building and adapting world models in a continual learning way. So in this setting, we're looking at specific sorts of worlds. They're broad worlds, but they're specific sorts of worlds. But if we're really looking at big worlds, then we need to ask ourselves, what happens when we kind of stray into places that really are not like what we've seen before? How can we adapt our world models in light of the fact that we're actually seeing things that are out of distribution in a certain sense to the world model, and we need to adapt our world model accordingly? I think that's still an unsolved problem and an interesting problem to look at, but it's a fundamental problem in continual learning because it's continual learning for generative models. And why is continual learning for generative models more of an issue? Well, it's because actually doing the correct thing involves erasing the information you've learned before. If I'm in a new setting and I've got a new data distribution, then rightly, the things that have low density, I'm pushing to zero. I'm trying to get those as being low density. So I'm trying to erase the things that previously had high density and now have low density. If I want to really maintain the distribution over the whole of history, I need to be explicit about that and have that as explicitly part of my objective, because the objectives we're using at the moment are not doing that. So building and using adaptive and adapting world models is a continual learning problem. The other thing is, let's move beyond irrelevant test settings and build interesting environments that allow us to test continual learning challenges. And that's another thing I think it's kind of key to work on. Here we've been working on a kind of multi-agent, kind of embedded environment for testing multi-agent cooperation and how we learn that. And in a certain sense, these are very long horizon problems. They involve pulling up information from different places, and it's quite an interesting setting to look at things in. So I guess in summary, what I'm vaguely saying here is that there isn't really such a thing as a continual learning problem. So that is, we're continual learning people targeting real problems with a continual learning mindset and trying to understand how we can make things better by focusing on the things that we think matters in those sorts of settings. Let's stop trying to kind of work on things that really miss where everyone's at the moment and move on from that. And so let's have a look at what other people are doing and ask, well, what is the continual learning issue in this particular situation? Because when you take a look, it's almost invariably there, and try to think of things in those terms. And at the end of the day, this kind of lens of lifetime learning is a powerful one because it's a big problem. And how do we tackle that? How do we kind of keep things moving in that sort of sense? So that's me. That's really what I want to say. I probably have about 30 seconds for questions because I've overrun a little bit, but thank you very much for listening. Over to you.
Thanks, it was really interesting. And one of your earlier slides, you've mentioned using KL distribution.
Yep.
So again, that's an output level metric, which is one we will also kind of use that just in a presented here. So have you thought about, or have you tried to look at the internal representations of of the layers to see
Yeah.
what's going on there?
So I think that, so yes, but I think that's a mistake. And the reason why I think that's a mistake is that all sorts of things can happen internally. And some of them can be completely irrelevant. I can have a learning method that, it takes a picture of Keir Starmer and injects it into my representation space. And then later on, it goes, oh, actually, Keir Starmer is irrelevant now, and I need to remove that there. But if my problem was nothing to do with Keir Starmer, then I've got a situation where I have looked like I've learned something, and looked like I've forgotten something, but none of that mattered in terms of the problem I was tackling. That came out a little bit more political than I meant it to. Don't interpret it that way. So I think when you start looking at things in representation space or parameter space or all these spaces, things are so entangled, it's not clear what the implication of change is. For example, in a neural network, I could have changed to an identical function space, but where all the parameters are different one another just by switching parameters over. It looks like a completely different network, but it's not. It's functionally equivalent. So function space is the space to work in, and the function space we care about here is that long-term joint outputs of how it's going to do on everything it needs to do things on, because those are the things that matter. So that's my take on it. I mean, I'm always happy to argue with people if you come at it from a different perspective. So that's great. And yeah, that's our angle. I'm sure there are other people who could argue good angles in other directions there, but that's where we're coming at it from at the moment.
Another comment. I think my good overall takeaway, there's a lot of stuff that's being presented in this. Briefly, I guess grounding is sort of briefly went over because you're trying to resolve the drift problem caused by bad hallucinations. And I think my takeaway is bad hallucination could be because you're not controlling the knob of forgetting quite accurately. Is that what's causing?
Sorry, in what are you talking about in the world model context here?
Yeah.
So that's not my take on it, but I could be wrong. My take on it is it's the usual problem that there is a mismatch. There's a kind of model mismatch to some extent compared with reality, and what you have in any sequential modeling problem is the problem that I'm now generating data, which is slightly out of distribution compared with the data I was trained on. That increases my uncertainty, and then when I start conditioning on that data in the future, because I'm now out of distribution in what I'm conditioning on, and that therefore increases uncertainty. So you get this kind of process there. So I'm not sure that's too much about whether or not I'm forgetting well. It's more that, in fact, I'm not remembering well, in a sense I'm not collapsing things down to the space of things that I believe I have seen.
So the way that's usually solved in at least robotics and sun systems, for example, it's loop closure, right? So you can essentially sort of reinforcing a loop and eventually collapse the right stateful representation. What would be the alternative to doing that for grounding?
So I mean, I think there are a number of key things there. One of them is, so loop there is, if you think about what you're trying to do, you're trying to say, I need to understand what happens when I condition on things, even if they're things that I might not have seen before. And so what we do here is we actually instead train on data that is as we might expect to see it within the context of actually unrolling these things, so that we don't just treat this as a kind of full diffusion on the whole vector space, but actually characterize what we're conditioning on when we've seen it and have different kind of diffusion rates for different parts of it. So there is some element that basically we just need to model things better out of distribution in these particular settings. So you're still getting a joint distribution over that. But the other side of that is, there are a lot of other interesting directions on that. One of them is actually things like, symplecticity. So there's interesting geometric properties that things have that can keep things close to data manifolds that we care about. So there are lots of tools that we have in the bag that we could use for these sorts of problems. I'll be very interested to see what ends up bubbling up as the key ones that really make this kind of work in the long run. Great. Thank you very much.